Swayam Prabha. Digital India. Educated India.
Right. So that's that. So that we have seen this one. Okay. So now we have seen summation blending. One of the drawbacks with summation blending is that there is this bulge that happens. And so, for example, in the bottom left figure, what you see here is, you have these three skeletal elements and their implicit fields defined, around those. If you add them and you bring them closer, you see this bulge coming in at the center, and that's because you just added up those implicit values. So these implicit values got added up and the zero level set swelled up, right? So how could you avoid that? You could avoid that by defining convolution surfaces. And this is the same convolution that you might have studied earlier in your signal processing or even otherwise. And this bulge can be eliminated by defining a convolution surface. I think I have some more details, but then that's the form of the convolution. It is defined in terms of two functions, g and h, where h I believe is known as the kernel function, and g is my other implicit function. So you convolve it with a kernel, and then you eliminate the bulge. And convolution is the same convolution as it is defined classically. And yeah, this is some recap of convolution in case you want to see. But then a kernel is just another function. We call it kernel because that's not the main signal. It's an auxiliary function that we convolve with, right? So a kernel is a smaller function that, it's an auxiliary function that you convolve the main function with, right? So for example, in this case, you have a function f and a function g, and I believe g is the kernel function, and then you convolve, you get, depending on the order, you get a different output. There is another operator known as the correlation and convolution, right? Very similar names, but then slightly different purpose. You had one more question. So don't bother if you haven't read about it, but yeah, signals theory talk a lot about convolution. You could say that a kernel is another, it's a shorter signal, you could say, right? And it's usually a shorter function that you can convolve with. So right, so the making of this hand is then defining various skeletal elements and placing them at the right place. So for example, fingers, the skeletons, and the veins, the base of the hand, the palm, they all have different skeleton elements, and then convolved together with a kernel function. Usually kernel functions allow you to in this particular case, they would allow you to glue all of these things together without leaving the creases, right? But then the convolution is having the standard sense of convolution. Now, these skeletal primitives may be a little tricky to define for complex geometries, but for simple geometries, they're quite easy to do. For example, we already discussed about some skeletal primitives like the line, segment, point, discs could be one. I believe I have some examples here. So for example, line segment primitive AB can be defined, the field around that could be defined in the form of a capsule or a cylinder with hemispherical caps, right? So we saw it for a 2D. Remember, I drew it For a 2D line segment, for a 3D line segment, you define it similarly. But what you get is a capsule-like level set for that. And the distance computation, you could use some algebra to compute the distances. If you want, I can go through it, but this is some basic algebraic calculation here. Basically, you want to calculate the shortest distance. So remember, I said it's going to divide the entire space into 3 parts, 3 regions. The inner region is where you want to calculate the perpendicular distance between a point and the line, and what you see here in AC is exactly the perpendicular distance, right? CP naught in this case. Whereas AP2 is easy to calculate, it's just a point-to-point distance. So if you want to calculate distance between a line and a point, this is what you're gonna get, right? All right, so these are some of the distance fields defined on these primitives. Could somebody guess what the primitives could have been? Do you recall? Can you guess some primitives? So you could see that the first one, it was a cone, then it was then cylinder on the right, and I can move my mouse cursor to show you. And then this one is a disk, then a ring or a circle. So you can see that the distance field of a disk is different from a distance field of a circle. Because remember, the circle has no interior. The circle is just a one-dimensional curve. It's a curve in 2D or 3D, right? Whereas a disk is more like a sheet of paper with the circle as its boundary, right? Then you have a cube, a square, and a point, and a line segment. Okay, right? So these are some of the well-known skeleton primitives. So that was one way. So using skeleton, you can define these implicit surfaces. Now, another powerful concept when it comes to defining shapes in terms of implicit functions is the so-called constructive solid geometry, or CSG in short. What CSG does is that it defines Boolean set operations on implicit functions. Well, you can also use it to define Boolean operations on meshes, but it is very, very easy and straightforward to do Boolean operations on implicit functions, and we'll see that now. So Boolean operations defined for implicit functions, and it becomes a binary tree where the leaf nodes are polynomial primitives, or the implicit fields for, let's say, some typical skeletal elements. The internal nodes are Boolean set operations, right? So any internal node will take 2 implicit surfaces and will do something onto it to create a third implicit field, right? What it will do will depend on the operation that it supports, right? For example, some of the Boolean operators are union, so you may want to take a union of those 2 fields. You may want to do an intersection, right? Or you may want to do a difference, that is, cut out one implicit field from another implicit field, right? So these are some of the operations that you can do. And this is how it looks like. So you have notice here that on the leaf you have primitives like a cube, sphere, and cylinders, and you can combine these using these Boolean operators. For example, you could say, I want to take a union between these 2 cylinders, and you get this new implicit function, an implicit field. Then you can take a union with another cylinder, and you get a very interesting shape like this. on the other end of this tree, you have a sphere and a cube, and let's say, let's say you take a intersection in this case, not the union, right? The intersection is the common volume between these two primitives, right? And that's how it looks like, right? So you have the red and the green objects here, and let's say you wanted to carve out the interior of this sphere and cube intersection from this cylindrical complex, right? You take a difference and you get a very nice 3D modeled object from just using Boolean operators of these, right? Okay, we have a quick question, I believe. Even the orientation is affecting the individual component. What can you elaborate? What do you mean by orientation here?
The cylinders. So actually, cylinders are actually the same cylinder which is being like
Oh no, well,
put
no,
through
these are
a
not same
union.
cylinders. These are cylinders along different axes, and you can define the cylinder along any axis you want.
Okay,
Right?
those are
So,
separate ones.
yes, of course. Right. So how do you define a cylinder? You define a cylinder with a axis, a 3D vector, and a radius around it, and of course the starting and the ending of the cylinder. Right. So in this particular case, this simple case, it's the XYZ axis, and then I define cylinders around it. Okay.
Yes.
Right. So that's CSG, and right. So mathematically, how could you define these Boolean operators, union, intersection, and difference? The union is easily defined by taking a max of all the implicits. In this case, in a CSG, we have only two because this it's a binary operator. But in general, a union can be taken on k implicit functions. In this case, in our case, k equals to 2, right? So you just take a max, and that's my union, the max of the implicit function value, right? Because there is no explicit surface; it's all implicit, right? So basically, you have values for every point in space, right? So if you want to calculate the resulting field, what you do is you have two input fields and you want to calculate the output field. What you do is you take a max of the input fields at a point, and then the max defines the final value, right? So for every point in space, you do the same. You keep on calculating the max, and then with the max, if you do a zero level set, you will get this union of these two fields. Exciting, right? So you just do a max and magic happens. Intersection, on the other hand, is the min operator. So you take a min of all the fields at the same point, you get the intersection. The difference is a bit complicated. The difference is defined in terms of the min-max operator. And so basically in this case, you can assume that because this expression will become more complicated, assume that you have two fields, F0 and F1. So what you could do is you do a min of F0 and this 2 times ISO value is the ISO value that you want to, the ISO value of interest, which in this case is 0. So you do, and it could be anything as well, right? So you do F0 and max Fj is just Fj. So F0 and minus Fj, you take a min of that, right? And that's my min-max operator that calculates the difference. Must be noted that these CSG operations, they create creases. So there are C1 discontinuities. The derivative is no longer C1, no longer defined along the creases. So you have a sharp crease, and the sharp crease, to be frank, it might be needed in certain applications, right? I mean, I might want a sharp crease at a point. So it's a It's not an artifact of CSG, but rather it's a good thing. You actually want creases, because implicit modeling by itself doesn't give you creases because it deals with smooth functions, right? So CSG allows you the capability to create creases in these implicit functions. Okay.
So, sir, can we say that to construct the complex geometric shapes 3D, we are using the basic shapes and applying Boolean on them to get the complex structures?
Yeah, exactly. So to define a complicated shape, you define simple shapes with these implicit functions, and then take a union of take these use constructive solid geometry to define them very complicated shapes. In
And
fact,
sir,
there are
on
yeah.
generating the basic shapes, we are generating it by the distance function, right?
Yes, so basic shapes are almost always generated using the distance functions. And remember, on top of the distance function, we distort the distance function with the fall off filter function, right?
Right.
You may or may not want to do that. That is usually done when the distance function is an unsigned distance function, right? I think I didn't mention this before, but in implicit modeling, usually that distance function was unsigned. When I have a signed distance function, I need not do that, because well, it depends on the application, right? A distance or a signed distance function will have a 0 value at the skeleton. The fall of filter function inverts that. The fall of filter function says that the highest value is at the skeleton, and then it tapers off. So I actually might want that, right?
So if we do that, then the maximum structure, the most highlighted structure will be at the periphery of the original structure.
Yes. Yeah. And you define how much how far you want to go from that
weight of at the skeleton.
Yeah. Yeah. Okay. All right. Okay. So that's solid constructive solid geometry. Sign distance field, I have already explained you. It's the same idea as distance field, but we attach a sign based on the inside outside with respect to the surface. So given a surface S, you compute the shortest distance from a given point, and it's the same expression, but you need a way to figure out the sign of the distance, right? And in a discrete setting, you almost always compute it on a set of pixels or in a volumetric grid. So pixels as it in a 2D image, or volumetric grid, which is in a 3D, right? You may also want to compute it over triangles or tetrahedrons. And tomorrow we will have a lab where the TA will take you through an exercise to calculate sign distance field on a volumetric tetrahedral mesh. Okay, don't worry if you don't understand what is a tetrahedral mesh. We'll cover that tomorrow. All right. So yeah, okay. I talked about tet mesh, and here it is. Right. So this is an example of a signed distance field. A usual computation of signed distance field is O(n) square in 2D and O(n) cube in 3D, because I'm iterating over all the points in the space times all the points on the surface, and the dominating the dominating computation is iterating over all the points in space, right? And because I'm in R3, it's a n cube complexity, and if I'm in R2, that is in 2D space, I have O(n)2 computation, O(n) square. So right, so for example, in this case, you see a cutaway section of a dragon mesh. Well, I don't know if it looks like a dragon to you, but it was a dragon. And then we computed a distance field over the dragon on a tetrahedral grid. So there are tetrahedrons all along inside, and then for every vertex of the tetrahedron of all tetrahedrons, we computed a distance value from the surface, and that's precisely we'll do in tomorrow's lab. So you'll have it in action. Right. So we have been talking about implicits and distance field, sign distance field. Let's talk about how do I recover the shape. So starting from a shape, I can convert it to its implicit function. But then given its implicit function, I can also recover the shape back. And how do I do that? The level set is the answer. The level set of an implicit function is defined as an isocontour. So whenever you hear the word isocontour or isosurface or level set, same thing. Basically, you carve out a surface from that implicit function, right? In a sense, this is a surface on which the implicit function attains a certain constant value, right? For example, the zero level set is a special case, right? We have seen all the points that satisfy fx equals to 0. In that case, 0 is the level set of that implicit function. And I can also compute the normal at any point x, and as we saw earlier, it's defined by the gradient of x, and you normalize that. So it sounds good, but how do you compute the level set, right? The level set, there are certain methods to compute the level set, depending on what you want, but most often or not, you want a explicit representation or a discrete representation. That is, you want a triangle mesh out of my implicit, right? Because implicits, you need to visualize, you need to see what you have defined, right? There are a couple of ways in which you could visualize a level set. And one of the ways is to convert it into an explicit mesh and then display the triangles that you have obtained. Okay. There are two main algorithms when it comes to polygonization. One is known as the marching cubes algorithm, and the other is known as the marching tetrahedral algorithm. And as the name suggests, marching cubes marches through the cubes, and marching tetra marches through the tetrahedrons of the the domain that you have defined in the domain, right? So where do these cubes and tetrahedra come from? This is a test if you are attentive or not. Where do these cubes come from? Anybody who wants to answer?
Are they
Yeah,
from
marching
discretized? As in, are
Sorry?
they because we are like sort of discretizing that whole thing again? Like, does it come from that?
Right, exactly. Thanks. Good. You guys are attentive. I'm very happy to know. So we defined the implicit field, and I have been talking about defining a implicit field at points in space. But how many points in space do I need to consider, right? So let me share my screen again and draw a little bit. Right, right. So how exactly do you, which points? So which points to consider while defining the implicit function? Which fields should I consider? Can somebody suggest me? I am in a space, and let me come back to the original problem. I'm feeling very sweaty here. I'm very hot here. I want to turn on my AC and sit at 20 degrees Celsius, right? And I'm going to define this as an implicit function, find out, take a level set. But in the first place, where should I define my implicit? At what points should I define my implicit function? Because, if you see, the space around me, the room in which I'm sitting right now, is continuous, right? It's a continuum. And there are infinite points in this space. Which points should I pick up? Any ideas?
Like, we don't have an option but to like take random points which are probably equidistant from like along a line from you to the air conditioner probably.
Oh, but the air conditioner is one. Okay, so if this is the air conditioner, so that's the room. Let me draw a 2D diagram. Okay, this is that's my AC unit, air conditioner. Sorry for that. AC unit, right? And it blows air from this side. And I'm standing here. So which points should I consider when I want to sample the temperature? At what points should I sample the temperature? Can you repeat your answer?
Okay, I was saying that we might take a like straight line path from you to the air conditioner.
The
So,
straight line path from me to the air conditioner is this.
and then we'll
Okay,
take
then.
random samples from this particular path, as in
So random.
equidistant, so that we can get a good measure.
Okay, you mean uniform or random? Give me one answer.
Uniform points. As in, if we
Uniform is the
have,
answer.
yeah,
So uniform points. Okay, but that's not sampling the entire space. I'm only sampling along one line. What about the rest of the space? Because if I measure temperature at these points, I'll probably have to lift myself in the air to go to the 20 degrees Celsius temperature point, which is
oh,
not possible in the current setting.
yes.
So what about the other points? Maybe it's a good idea to sample other points as well in the space, because I'm hoping that some fluid mechanics guy can tell me, but probably the air is going to go down like this and probably circulate something like this and maybe like this. So my chances of getting hot cool air might be here. So I should sample that point, and in fact, I should sample all the a lot of points in this space, and then do a level set, and then figure out uh, what is the best place to sit, right? So which points should I sample?
So then we don't have an option but to sample the whole space.
Right, and what would be my strategy?
Then that would be like creating a sort of mesh, 3D mesh in real world, but in the diagram 2D, I guess.
Okay, 2D mesh, and where do I get the mesh points? That was my original question, right? Mesh is fine, but I need points at which I can calculate the distance function, the implicit function.
Okay.
So we could consider an origin at a corner of the room, and then at equal distance we can take points away from it
Yes,
in all the directions,
right.
and
So
then
what do you
in
mean
that
all the
range we
directions?
can calculate. So
Okay,
like
are these the directions?
no sir, so along so we can take axis like x-axis, y-axis, and then z-axis if the room is in 3D, and then
Yes.
vary the points in regular intervals and form a grid sort of thing, like the mesh we were
Aha.
talking about, and then check
Okay.
those points.
Wonderful. So yeah, that's what I was looking for. So one strategy is to regularly sample. So I create a grid of points like this, and let me just complete that. So a horizontal set of lines, and then just to complete it, I'm gonna create a vertical set of lines, and this will give me a set of grid points, right? And this, you could also say a pixel grid or just a grid, a regular grid. I think pixel grid is not a right word to use here, right? So this is a grid, and then you get these points. These could be my sample points, the intersection points of these, right? And then you can measure temperature. Let's say you have some device that can fly in the air and measure the temperature. By the way, you could fly a drone with a temperature sensor, for example, and then get the temperature, and then once you have everything set up, then you can do a cross section and then find out. So this is the grid that we are talking about. Similarly, you can define in 3D, you can define a volumetric grid, right? In 2D, This is called pixel grid, or just a set of pixels, right? What is a pixel? A pixel is a picture element, pixel grid, right? I mean, pixel grid, you call pixel grid in the image processing literature. In the simulations literature, you don't call pixel grid, you just call a uniform grid. So I will write here uniform grid. And uniform grid is you can say it for both 2D and 3D. In 3D, it's called a volumetric grid. And these elements, individual, elements are called voxels or volume elements, okay? And then at the center of each voxel, you calculate the distance, okay? So these are your sample points. And tomorrow we will see that if you don't like uniform grid, you could also create a unstructured grid. Unstructured grid, which says that if you have a mesh, you could just use the vertices of the mesh to sample, right? So I have these blue points here. I'm not drawing it in full, but you can use these points to sort of sample. And this is in 2D. In 3D, what you have is a tetrahedral grid. Tetrahedral. Everybody understands what is tetrahedral in this grid? A tetrahedron. What is a tetrahedron? Anybody?
Pyramid.
Sorry?
Pyramid-like structure.
Pyramid-like structure. That's a good question. What is a pyramid? A pyramid is like this.
One less than that.
What do you mean one less?
The base number of lines in the base is one less, I guess, in tetrahedron.
Number of lines in a base. Okay, can we be a bit more
Triangle base having a pyramid-like structure.
Okay, triangle base with a pyramid-like structure. So can I say this is a tet?
Yeah.
Okay, my bad. I think I should draw it slightly better. Maybe like this. Yeah, that's a tet. Okay, so a tet has 4 triangles as its sides, and so 4 things, right? This is a tet. This is a pyramid, and there is one more thing which you might have studied, a prism. Right? A prism is like that. Okay. So prism. So please. Okay. So we use tets, and if you collect a lot of tetrahedron, tet is in short form, tetrahedron. Right? We use tetrahedra in 3D. A lot of tetrahedrons. The plural of tetrahedrons is tetrahedron. Is tetrahedra. We use a lot of tetrahedra to cover the entire space, and then at the vertices of these tetrahedra, you can calculate the distance value or the implicit function value. Okay, so these are the points at which we had calculated. But then now I want to recover my shape, so I want to calculate the row level set of this corresponding to this implicit function. So let's see what algorithms exist for that. All right, so polygonization, it's an algorithm based on numerical continuation, and basically you have a space divided into cubic voxels or tetrahedral grid, and you search for a surface starting from a skeletal element or starting from a point. Basically, you want to figure out all the voxels inside which there is a change of sign, and I'll tell you precisely how you detect that. So remember, if you have a sign, this usually works on a sign distance field or on a implicit surface that has both negatives and positives so that I can calculate a zero level set. Or if you are not interested in zero level set, you basically need to identify all the volume element or voxels in the grid that contain the ISO value. Okay, the ISO value could be 0 or anything else, but the voxels, you search for all the voxels that contain that ISO value. That is, you have a cube and the 8 corners of the cube, some of them are on the negative side or on the lesser side of the ISO value. Some of them are on the higher side of the ISO value. Then you select that voxel and then you queue it up for further processing, right? You keep on searching the neighbors of such voxels. And when you are done, you replace those voxels with their polygons. There are certain cases as to define, there are certain configurations that define how to convert a voxel with a given set of, values along the corners into its polygonal representation. So let's take a look at that. Right. So this is the search in 2D space. You start with a skeletal element or right. So you start with a skeletal element or you find out a pixel or a grid that has values on either side of the ISO value. I'm deliberately not saying 0 here because you might be interested in a non-zero ISO value, but I hope you can correlate it. If I am doing a 0 level set, then this box, the grid that I'm selecting, must have both negatives and positives on the 4 corners, right? So a grid has 4 corners in 2D. What I want to select is all the grids whose corners have at least one different value. So in case of 0 level set, at least one negative and rest positives, or at least one positive and rest negatives. Because if the grid has all positives, that means that the grid is completely outside the level set. And if the grid has all negatives, that it means that the grid is completely inside the level set. So I don't want to process those grids because they will give me no surface. I am only interested in those grids that have the surface passing through them, right? So in case of a 0 level set, while detecting a 0 level set, I need both negatives and positives as the corner values. And then I collect all of those. So if I parse through this entire grid, I will locate all the grids. Like in the last diagram, 4th diagram, you will see that I have collected all the grids that have both negative and positive. That is, the surface is guaranteed to pass through these grids, right? And in 3D, these grids would be cubes, the voxels, right? Now, depending on the number of positive corners and negative corners, or the lower corners and higher corners in the cube, there are different configurations of triangles that, or the surface passing through. Remember, we are triangulating now. We are converting the implicit field into triangles. So therefore, these are the functions. So there are a total of 256 possibilities, right? Because how many corners does a cube have? 8 corners. And then how many values are we considering here? 2 values, either the negative side or the positive side, right? So positive values could be lower than the ISO value or higher than the ISO value. So 2 possibilities. So total 2 to power 8 possible cases. But it has been noticed that a lot of them are similar cases. That is just change of orientation of the cube. Therefore, there are only 14 unique cases. Okay, and so let's quickly see the first case where, if you see the first, maybe I'll move my cursor now. Let's focus on the first cube here. And there's only one corner that's, let's say, positive and rest all are negative. That means that the surface most likely passes through like a triangle cutting the corner, right? The second case, for example, which has two negative values and rest positive, will have a surface that passes through, that cuts the edge of the cube. If you have two corners, opposite corners that are negative, this could be one configuration, and so on and so forth. So depending on different configurations, you have different set of triangles, right? Is this clear? The set of configurations. So 14 unique configurations, right? And that's it. So once you have identified such blocks and identified these topological configurations of triangles based on the values, the only thing that you need to do now is perform a linear interpolation and figure out the coordinates or the vertex coordinates of the triangles that pass through. And fortunately, these vertex coordinates will always lie on the edges of this cube. So essentially, you need to do a linear interpolation on the edges. So for example, in this case, the edge that has V2 and V6 as the values, you want to find out. So V2 is some positive value, V6 is some negative value. You want to find out where exactly was 0, right? So this is equivalent to performing a linear interpolation. You find out, because you don't know what was the underlying function, it could have been any implicit function. What you want to find out is, the best you can do is just assume that it was linear. The function was, assumed linear within that box, within that cube, and just perform a linear interpolation to figure out the value of A. And the way you do it is with simple linear interpolation. Okay, and I think that's pretty much it. I hope. Yeah. So one more thing. So there are a couple of problems with marching cubes. Is that there could be some ambiguous cases, for example, and this particular case, you have two opposite on a face. You have two corners that are positive, two are negative. Then you can have any of these configuration. You don't know which configuration you should take. This is an ambiguous case. So how could you resolve it? You could resolve it by doing an additional sampling at the center of the face. That will resolve the case. Or what you could do is, instead of marching cubes, use marching tetrahedra. And marching tetrahedra does not have any such ambiguous cases. By the way, you can split a cube also into, I think, 4 tetrahedra or maybe 6. But anyway, you can split a cube into a number of tetrahedra and then go ahead. Another problem with marching cubes is undersampling. If the function varied too quickly, the voxel will not capture. This is a sampling problem, right? Remember, we said that we need to sample sufficiently enough. In this case, there was no sufficient sampling. So you don't know what your function, your surface will miss out on these details because you never sampled it, right? So these are the sampling problems associated with marching cubes. So that's all for today. These are some of the references that are important question. But all right, great. So if no more questions, then thank you very much